I'm Henry DeYoung, and I'll be talking about parametric subtyping for structural parametric polymorphism, which is joint work with Andreia Mordido, Pfenning, and Ankush. Recursive types, parametric polymorphism, and subtyping are ubiquitous in modern programming languages. For example, the type stack alpha uses the first two of these features to describe stacks of elements of type alpha. In other words, a stack is an object that offers push and pop methods, where the pop method uses the auxiliary constructor, maybe kappa, to account for the possibility that the stack may be empty. Sometimes we might wish to ensure that a stack is used according to a specific protocol. For example, when implementing a queue with two stacks, all pushes should occur before all pops. This protocol can be described by the pushes beta and pops gamma type constructors. Whenever the first pop from a stack of type pushes beta occurs, the remaining stack has type pops beta, which does not offer a push method. According to the usual rules of structural subtyping, stack alpha is a subtype of pushes beta whenever alpha and beta are mutual subtypes. The direction of this subtyping holds because any stack that implements all of the operations can always be used in the specific context where a client expects to use only the operations described by pushes beta. Similarly, stack alpha is a subtype of pops gamma whenever alpha is a subtype of gamma. In other words, these two inference rules are admissible. Unfortunately, the combination of recursive types, parametric polymorphism, and subtyping is difficult to manage. Prior proposals include the material shape separation and the prohibition of contravariance. In this paper, we propose an alternative, a notion of parametric subtyping. The slogan for parametric polymorphism, in the style of Reynolds and Girard, is that related arguments are mapped to related results. Inspired by this, we propose parametric type constructors that follow the modified slogan, related type arguments are mapped to related type results. Parametric subtyping is then the fragment of structural subtyping based on these parametric type constructors. It has several advantages, including its decidability and it being intuitive, having a relatively simple declarative characterization in terms of infinite derivations. That's the essential idea, but we can look at some specifics. It's helpful to first review a saturation-based decision procedure for structural subtyping of recursive types without parameters. Even and odd natural numbers are a simple example where even and odd should be subtypes of that. To verify that even is a subtype of that, backward proof construction would usually be used. But here we will use saturating forward inference because that's what will generalize to parametric subtyping. We will assume that even is a subtype of that and try to find a contradiction by inferring more and more consequences of this assumption. If we've reached saturation by inferring all of the consequences that we possibly can, and we still haven't uncovered a contradiction, then we will know that even is indeed a subtype of that. Expanding the definitions of even and that and appealing to inversion on the structural subtyping rules, we arrive at the consequence odd subtype of that. We can add on subtype of that to the database because it involves two type names. And then we can consider it once more expanding and appealing to inversion, inferring the consequence even is a subtype of that. However, this even subtype of that is subsumed by the existing one. So at this point, we have reached saturation. No new consequences can be inferred, and because we still haven't uncovered a contradiction, we conclude that even and odd are indeed subtypes of that. Stated differently, even is a subtype of that, and odd is a subtype of that are admissible subtyping rules. Here, saturation is guaranteed because a given program uses finitely many type names. Notice in particular the property that no pair of type names was expanded more than once during this algorithm. Unfortunately, once we have recursive type constructors, we can't just use this same algorithm to decide structural subtyping. Saturation isn't guaranteed anymore because constructors make it possible to infer infinitely many pairs of types, such as T of that is a subtype of U of that, T of that is a subtype of U of that, and so on. In fact, we proved that structural subtyping is undecidable for recursive type constructors by a reduction from the simulation problem for basic process algebra. A related proof for a different problem has been given by Padavani. What can we do? One option is to impose a bound to cut off forward inference and force termination when the bound is reached. A major disadvantage of this approach, however, is that the accepted subtypings would then depend on the vagaries of the algorithm, making it very difficult for the programmer to understand and predict what are the accepted subtypings. It would be much better to find a fragment of structural subtyping that has a relatively simple characterization and is decidable. This is where our notion of parametric subtyping comes in. Recall the admissible subtyping rules from the stack protocol. The key observation is that these rules are parametric in the sense that related type arguments are mapped to related type results. For example, this rule is parametric because it maps related type arguments alpha and beta to related type results, stack alpha and pushes beta. Thus, parametric subtyping is the fragment of structural subtyping in which the accepted subtypings are exactly those that hold parametrically. As a non-example, a monomorphic type that stack would not be a subtype of pushes beta under parametric subtyping because it would necessitate relating a type argument beta to another non-argument type that. This means that parametric subtyping has the flavor of a subformula property. Even though structural subtyping is undecidable for recursive type constructors, parametric subtyping is decidable. The decision procedure consists of two phases. The first phase is saturating forward inference to derive admissible subtyping rules, much like what we did earlier for even and odd. The second phase will then use backward construction of derivations from these admissible rules. To demonstrate, we will verify that stack alpha is a subtype of POPs gamma whenever alpha is a subtype of gamma. As before, we will make an assumption about stack alpha subtype of POPs gamma. but this time, instead of assuming stack alpha is a subtype of POPs gamma outright, we will progressively refine a set of constraints on alpha and gamma imposed by stack alpha subtype of POPs gamma. Initially, the constraints are trivial, represented by top. Forward inference here leads us to deduce that maybe alpha cross stack alpha is a subtype of maybe gamma cross POPs gamma. At this point, parametric subtyping means that we don't expand, but we instead consider a new parametric question about maybe kappa and maybe kappa prime. Forward inference here leads us to kappa is a subtype of kappa prime, and we add this constraint to our set of constraints. Returning to the postponed judgment, we apply the information learned about maybe and infer that alpha is a subtype of gamma, and stack alpha must also be a subtype of POPs gamma. Alpha subtype of gamma is a new constraint that we add to our set of constraints, and then we can recursively apply this rule to the remaining stack alpha POPs gamma, which yields alpha subtype of gamma again. But this is subsumed, and we've reached saturation. Because we've saturated, the totality means that these constraints are also sufficient, and we have derived admissible subtyping rules. Once forward inference saturates, phase 2 involving backward construction begins. For example, suppose that we want to decide whether stack maybe even is a subtype of POPs maybe not, because there is at most one admissible rule per pair of constructors. We can build a derivation, and this algorithm is guaranteed to terminate. Forward inference in phase 1 terminates because there are finitely many parametric subformulas. Backward construction in phase 2 terminates because it is inductive on the structure of the types. As a further example of parametric subtyping, we can look at serialized binary trees. In Haskell, we could define the type of ordinary deserialized binary trees like this. The serialized form of binary trees would then be described by the non-regular type S tree alpha kappa. We can also define the types of spines and serialized spines as spine alpha and S-spine alpha kappa. Spines are particular trees, and serialized spines are particular serialized trees. Our algorithm verifies this in terms of these admissible subtyping rules. To summarize, the main contributions of this work are to prove that structural subtyping for recursive type constructors is undecidable, and to propose parametric subtyping as a fragment for structural subtyping of recursive type constructors that is intuitive, decidable, and practical. We have implemented the decision procedure and have made it available online. Possible topics for future work include extension to Curry-style polymorphism, bounded quantification, and subtypings due to the uninhabitedness of certain types. It would also be interesting to see if this might be useful at higher order kinds and to see whether parametric subtyping can be integrated with intersection and union types. Thank you very much for your time.
subtyping of session types, and we explicitly designed the system that it would capture that. And as you can see from the serialized tree example, this is actually a session type example that we reformulated in this style, because when you want to send a tree across a network, you serialize it, and then you deserialize at the end. And with these types, you can, the linear version of these types, you can type check this session type program.
Just following up from that question, I wonder if, in your experience, did you run into any obstacles based on the restrictions you have to be parametric? Were there any examples of protocols where you really wanted something more?
So there's two situations which come up in practice which you can't handle. So one example, if you have a type abbreviation, if you will, which is not recursive, so you might say an int pair is a pair of two ints. So you usually want to expand that type definition when you do type checking or subtyping rather than trying to treat it with this algorithm. And the other one is you have a very specific type like natlist, and you compare that to a list of alpha, which means your program was originally insufficiently general. And so usually in that case, you would refactor your code and you rewrite it in that style. So beyond those two kind of situations, we haven't really run into much that would be a problem.
Thanks.
We have a question from Discord. Can phase 1, the forward phase, be computed at time declaration time rather than at time usage time? Would that pre-computation be a good idea?
Yeah, so we don't pre-compute it. What you do is you compute it lazily. So when a given subtyping question is asked, you compute it and then you memorize it. So if the same question is asked later in the program, you have it there. Otherwise, you would pay order n squared essentially, or n cubed, if you do everything ahead of time. But you don't need to. You just memorize those that are actually asked, and then you go from there.
Okay, I think that's all we have time for. So let's thank Frank.
Okay.